Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge, minimum number of 1-bit operations to make integers 0. So let's first explain what it is. So you get a number n, which represents a binary. So for example, 3 represents 1, 1, and you want to get that to 0, all 0 in the binary representation. And the goal is to know what's the minimum number of operations to get it to 0. Now, what are the operations we are allowed to do? Only two operations. One is changing the rightmost, which is the 0th bit to n, of n, basically changing that bit. Now, notice here they say change. By change, they mean change it either if it's 0, changing it to 1, or if it's 1, changing it to 0. So both are represented by this operation. And here by the 0th bit, be careful to not be confused here, because you might think it's this one, the 0th bit, but it's not. This is the 0th bit. It's the last one here. So basically the direction is like this. So this is the 0th bit, this is the first bit, this is the second bit. Okay, and so basically it means you are allowed to change the last bit, but only the last bit in one of the operations. The second operation is you are allowed to change the ith bit if the bit before it, remember before it is in this order. If the bit before it, so you can change, let's say if you had 0, 1, 1, 0, 0, then you can change this here because the one before it is 1 and the ones before that are 0. So you can only change it if the one right before it is 1 and all of those before it are 0. Okay, so we clarified that you can change the ith bit only if the one before it is 1 and the ones before that are 0. Notice that if, let's say, we had something like this, we can still change this bit, because if there is nothing before it, we can consider that like if it was all zeros. Okay, so those are the only operations we can do. N is pretty big, so we need to find an efficient solution. But let's take a look at the examples and see if we can find the pattern. Okay, so first let's look at a couple of observations. So we know that at least for the first bit, so let's say something like this, if it was 1, then this is one operation, we can change it to 0. So for the first bit, it's super easy. Now what about if we had something like this? Okay, how do we change something like, let's even make it simpler. How do we change something like this to 0? Well, we can't use operations 1, which basically means you can change the 0th bit. We can't do that because if we do that, we can't do that, but that would not give us 0 alone. The operation 2 says that we can change the ith bit, but only if I minus 1 bit is 1 and before that it's all 0. Okay, so to be able to use operation 2 to change, because that's the only way we can change a bit that is not in the 0th position, we would have to change first the I minus 1th bit to 1. And lucky for us, that's easy because we can just use operation 1. So we can use operation 1 to change this to 1, 1. And then once we do that, we can do operation 2, because now we have the condition that we need here. Then we can change that to 0 here. And now this is operation 1. This is basically 2. Yep. And then now we can change, using operation 1, we can change this to 0. Okay. Okay, so seems like we need to apply operation 1 to be able to apply operation 2, and then we can apply operation 1. Okay, so we apply operation 1 to be able to apply operation 2, then we apply operation 1. Okay, so now let's take a look at another example. Let's expand this a little bit. Let's say we have 1, 0, 0. So what do? Well, we need to get this one to be 1 so that we can change this one. And so we take operation. Can we do it right away? We can't actually, because we can only use operation 2. So let's apply recursively. We have to change. So before we had to change this one to 0, but we can't do that until this one is 1. Until this one is 1. And so now our assignment is to change 0, 0 to 1, 0, right? How do we do that? Well, to do that, we already sort of did that here, right? We just changed 1, 0 to 0. Why is this one the same as this one? Because remember, change here means you can change 0 to 1 or 1 to 0, okay? So they are pretty much equivalent, because in one operation you would change 0 to 1, and then in the other one 1 to 0, right? So these one are equivalent. So so we already know this one takes 3 operations, and so we can just take 3 operations to get to 1, 1, 0, okay? And now once we get here, what we can do? Now we can apply operation 2 to change 1, 1, 0 to 0, 1, 0, okay? But now, notice, now we are back. This is the same as this one. And we know this takes 3 operations to get to 0. And we are done. Okay, so this is, how much is this? This is 1 operation. This was 3 operations. So basically what we needed here are 3 multiplied by 2 plus 1. But how can we sort of write this in a more structured and formal way? Well, if you look at this, actually this is recursive, right? Because what's this relationship between 1, 0 and 1, 0? It's just this one is the k. Let's say the kth bit is set here. This one has the k minus 1 bit set. So it's just you take the kth bit set and you subtract minus 1, right? And so you notice here, let's call this, for example, let's say this is the j minus 1 bit and this is the jth bit, right? And let's keep k. Let's say this is k minus 1, of course, because it's 1 position to the left. We start numbering from the right, so 1 position to the right. So what is this here? If we sort of use a function, then this is f of j is how many? It's 3, which is 3 2 times is just f of j minus 1 multiplied by 2 plus 1. That's exactly what we got here. You could try multiple examples to see if this works, but you will see that it works. That's why it's very useful to try multiple examples and try to see a pattern. Okay, so now we have the formula for when only 1 bit is set. Okay, so this formula applies when only 1 bit is set. Okay, basically the jth bit. So what this says, what this f of j is, number of operations to convert 1 0 zeros at the jth position to 0 0 0. Okay, so only 1 bit is set. Now our problem is, what if multiple bits are set? Here we had only 1 bit is set. So let's take the simplest example we can. So 1 1 0. So how do we convert this one? Well, notice this, since this here that we just calculated has the minimum number of operation, you can notice here this number is actually part of the steps that we do to get to 0 here, right? So what does this tell us? Well, let's see here. So what this tells us is that to get this to 0 is just this number of operation, right? So we just need to subtract what it took to get here, right? Okay, so how do we write that? Let's call it the function for converting 1 with multiple bits set. Let's call it p. Now, what do we want to write it in terms of? The only one we already have is f of j that we can pre-calculate, and so let's try to write it in terms of 1 bits set. So what is this? Well, this is actually just converting what is 1 0 what is 1 0 0 to 1 1 0. Well, this is just first you have f of, this is f of 0, 1, 2, f of 2, right? And this portion here is f of 1, okay? So this is actually just f of 1, 0, 0 minus f of 1, 0, because that's what we want to get rid of. We want to get rid of the number of operations that it took us to get to 1, 0, right? And the number of operations it took us to get to 1, 0 is just 3 operations here, which is the number of steps for 1, 0, right? I hope that was clear. So the number of steps it took us to get from this here to this here with 1 is just the number of steps. We don't need to convert this to 1, 0 because we already have 1, 1, 0, and so we can just subtract that. And how many steps to get to from 0, 0 to 1, 0 is just the f of 1, 0, right? So but f is written in terms of the jth bit set. So this is actually f of 0, 1, 2, f of 2 minus f of 1. And we already have the value, so we can just plug it in and calculate it, okay? But now I had only 2 bits set. Let's look at even more complicated. Let's look at one with 1, 1, 0, 1. Okay, so here it's easy because, okay, maybe to complicate it even more, let's do something like this, yeah. So in this case, what do we need to do? Well, first we know that we can convert, because when we have 1, 0, 0, 1, 2, 1, 0, like this, first to be able to set this one to 0, we convert this one to 1. So we need to convert this one to 1 and then do all the operation to get to 0. So we need to subtract this operation because we already have this. So how do we subtract it? Well, it's just 1, 0, 0, 0, 0. So basically the number of operation it takes for 1, 0, 0, 1, 0 is just the f of the entire thing, so 1, 0, 0, 0, 0 minus f of the smaller to get the 1 here, so 1, 0, 0, 0. But then what about this 1, 0? Well, this 1, 0, getting it to 0 is also something we already have, so we need to subtract it. So we need to also subtract, this is by the way between parentheses, so we need to also subtract 1, 0. And remember, this is 0, 1, 2, 3, this is f of 3, this is f of 1, okay? And so now if we expand this, then we have minus f of 1, 0, 0 plus f of 1, 0. Okay, so this is where you start seeing the pattern where we are just going through in order like this, right to left, and we have a plus for the first bit, a minus for the second bit, a plus for the bit after that, and then if you expand this and try maybe something like 1, 0, 0, 1, 0, 1, 0, you will see that the next one would be a minus, and if you add a 1 here, the next after that would be a plus. So we are basically alternating signs. And so this is what this is pretty much our solution. We can just take out the number n, to go through all the bits, 32 bits, and just every time check if the bit is set in the previous, it's the first bit, then just add f of the position of that bit. If it's a bit before and before that we had a plus, we do minus. If it's the one before that was a minus, then we do plus. And that's pretty much it. Okay, I know it's tricky, but the main idea is to see this thing with the fact that you already have a 1 here, so you need to subtract 3 operations that you would have needed if you didn't have a 1, right? Yeah, so now let's code this up and make sure it passes. Okay, so let's code the solution we saw in the overview. So the first thing we said that we need f to hold the number of operations for each bit when it's the only one set. How many bits we have? 32. We know that the first one we can just use the first operation, so that's we have just one operation. And then for the other ones, since for each bit we need the previous position, we need to start from the lowest one and go up, right? Because for each j, we need j minus 1. We can start from 1 because we already did 0 up to 32. And then here we can just apply the formula that we saw, which says that if it's j minus 1 plus 1. Now, we don't need to check if the bit is set, because literally this function means number of operations. Basically, f of j means number of operations if the jth bit is set only, right? So by definition, it's set by definition of the function. Okay, so now that we have this, we can go through our range. But now we said, as we said in the overview, we want to go right to left. So right to left. And so this needs to start from 31, minus 1, minus 1, okay? And what do we want to do? Well, we said that we want to alternate between sign. So let's call this the sign. And let's start with 1. So sign starts positive, or let's actually start with true. Sign positive, let's call it. Okay. So sign positive means plus 1, and then we alternate between plus and minus 1. Okay, so now what we need to check is if the bit is set, because if the bit is not set, then we don't need to change anything. So we check for n to check if a bit is set. You just end it with j, with the position, and then you check if this is different than 0. This means basically the jth bit is set. Okay. Okay, so if that's the case, then we of course also need to keep track of the total that we need to return at the end, the number of operations. Let's call them actually operations. Okay. So here we said that if the sign is positive, we want to add, otherwise we want to subtract. So here, add, we want to alternate them, subtract. Okay, and we also want to alternate, so alternate the sign. So to do that, well, we just say sign positive is equal to true if false if the sign was positive. I'm writing it this way just to make it super clear. Otherwise, if it was not positive, we want to set it to true. Okay, so if the sign is positive, we want to add. So we want to add to the number of operations. What do we want to add? Well, we want to add just the j operations required to get this jth bit to be 0. And so that's f of j. Okay. And then we said here we want to subtract. So that would be minus f of j. Okay. We shouldn't basically do this if the bit was not set, because if we do that, then we will alternate even though we didn't add anything. So we should make this inside the loop, inside the if condition. And so now this works. Let's submit. And this passes, okay? Yeah, so the main idea is to draw it out, try it, see different patterns. Here, this problem is hard because it requires using multiple things, one for this f of j formula, and then the other one for the alternate sign here. Yeah, I hope this was useful. Thanks for watching. If you need help, reach out to me via Superpeer in the link below, and see you on the next one. Bye.